there's this incredibly old, persistent trope in mythology and fairy tales.
Oh, yeah.
You see it across almost every culture, really. It's the story of the genie in the lamp or, the monkey's paw.
Right, or some kind of trickster god granting a wish.
Exactly. And the premise is always that the mortal gets exactly what they ask for, but it's rarely what they actually want.
Because the tragedy in those stories is never that the magic doesn't work. I mean, the magic usually works perfectly.
Yeah, flawlessly.
The tragedy is always that the human didn't ask for it in the right way.
Right.
The phrasing was vague or the context was missing, and so the literal interpretation of the request just becomes a curse.
You ask for gold, and you're literally crushed under the weight of it.
Exactly.
And that fragility, the fragility of human intent, is exactly what you are dealing with today. Whether you are prompting a digital AI brain or, say, commanding a cutting-edge physical fabricator, the way you communicate your intent totally dictates the quality of your reality.
It is the ultimate translation problem, really. Moving a concept from the chaotic, sort of abstract space of the human mind into a rigid set of instructions that a machine can execute.
Without disastrous misinterpretation.
Right, without it crushing you with gold.
So, to explore how we actually solve that translation problem, we have two completely distinct stacks of sources on the table today for this deep dive.
Very distinct.
Yeah. On my left, we have a highly detailed, comprehensive guide on AI prompting best practices. This is specifically focused on extracting top-tier performance from large language models, like Gemini.
It's basically a masterclass in digital instruction.
It really is. And then on my right, seemingly from a totally different universe, we have an apprenticeship manual for a piece of hardware.
The Bambu Lab X1 Carbon.
The X1C. This is a machine that is fundamentally redefining industrial 3D printing. We're talking molten plastic, hardened steel, intense heat.
And at first glance, I know forcing a connection between a cloud-based chatbot and a desktop manufacturing plant might feel like a stretch.
It sounds kind of crazy.
It does, because one operates entirely in the realm of probability and text, while the other is fighting a constant battle against gravity, thermodynamics, and friction.
But if we strip away the medium, if we look past the glowing screen and the spinning motors, both of these systems require a mastery of specific languages.
Absolutely. Both demand highly intelligent, structured workflows. And most importantly for you, the user, both rely on relentless, iterative feedback loops.
So that is our mission today. We are going to map out how you can take a perfectly articulated abstract digital thought and drive it all the way down into a high-fidelity physical object you can hold in your hand. Okay, let's unpack this.
Let's do it.
Let's start with the purely digital side of that equation. Structuring your thoughts for an artificial intelligence. Because the text makes it abundantly clear right from the jump, there is no single magic spell.
Right, there's no cheat code.
You can't just type, "do my job for me," or "make this sound better," and expect a masterpiece. The source provides a highly structured framework instead.
It breaks a great prompt into 4 distinct pillars: persona, task, context, and format.
And I want to dig into the underlying mechanics of why this specific combination works, rather than just, treating it as a checklist.
Well, to understand the utility of those 4 pillars, you really have to visualize what a large language model actually is under the hood.
Okay, lay it out for us.
It is not a database of facts. I think people get that confused. It is actually a vast, multidimensional vector space.
A vector space.
Yeah. Imagine a universe where every concept, word, and stylistic tone ever published on the internet exists as a coordinate.
Wow.
When you ask a generic question without providing a persona, the AI is effectively searching that entire infinite space or the most statistically likely next word.
So it's looking at everything at once.
Exactly. It's drawing upon high-level academic physics papers, terrible internet poetry, corporate press releases, and Reddit comments all at the same time.
Which means the output is going to average out into this bland, generic sludge.
Right, because it's trying to appease every possible context simultaneously. It basically defaults to the mathematical mean.
That makes so much sense.
But when you establish a persona, for example, the source uses the phrase, "You are a seasoned advertising writer." You are instantly drawing a bounding box around a tiny, highly specific neighborhood within that infinite vector space.
You're fencing it in?
Yes. You are instructing the model's attention mechanism to ignore the academic papers and the poetry, and to heavily weight the linguistic patterns, the vocabulary, and the persuasive structures used by top-tier marketing professionals.
So you are artificially altering the probability math before the AI even reads the rest of your prompt.
That is exactly what you're doing.
Okay, so if the persona sets the boundaries, the task is the directional momentum, right?
Right.
Because the example in the source asks the AI to create a concise tagline. We aren't writing a white paper, we are writing a tagline.
You're giving it a specific job to do inside that bounding box.
But the third pillar, context, is where I think, honestly, most people fail.
No, absolutely.
The prompt feeds the AI this really specific information. It says the washing machine's features are that it gets clothes extra clean, has 25 customizable settings, and fits in a small space.
Very specific.
But why is it computationally necessary to spoon-feed those features to a machine that has literally read the entire internet? I mean, doesn't it already know what a washing machine does?
Well, it knows the generalized concept of a washing machine, yes, but without that specific context, the AI falls right back into that mathematical mean we just discussed.
Oh, it gets generic again.
Exactly. It will generate generic marketing speak like, buy this washer, it cleans your clothes.
Which is terrible copy.
It's awful. But by providing the unique selling propositions, like the 25 settings, the compact size, you are giving that localized, seasoned advertising writer persona the actual raw tokens it needs to map against persuasive sentence structures.
You are grounding the probability model in your specific immediate reality.
Precisely. You're giving it the raw materials to build with.
And then we hit the fourth pillar, the ultimate constraint format.
The output filter.
Right. The prompt dictates the tagline should use an active voice and be no more than 6 words.
Which is a crucial step.
Because you could have a brilliant persona, a clear task, and incredible context, but if you don't dictate the structural output,
The AI might generate a beautiful, highly persuasive 3-paragraph essay that is entirely useless for a billboard.
exactly, constraints act as an output filter.
By demanding an active voice and a strict word limit, you are forcing the model to discard thousands of potential pathways that just don't fit that highly rigid syntactic structure.
So combining persona, task, context, and format transforms a vague wish into a highly engineered set of coordinates.
It takes the guesswork out of the magic.
But the source introduces another layer of instruction called the 3 C's of prompting. Be concise, be clear, and be consistent.
A very useful mental model.
Concise and clear make intuitive sense. Don't ramble, but I want to push back aggressively on the third C, be consistent.
Okay, let's hear it.
The text explicitly warns against changing your vocabulary. It says if you refer to a spreadsheet in your first prompt, you have to keep calling it a spreadsheet. You shouldn't switch and call it a matrix or a tab later in the conversation.
Right, that is a very deliberate directive in the text.
But wait, if this AI is supposedly a state-of-the-art neural network capable of passing the bar exam, why do I have to treat it like it has 0 reading comprehension?
It does seem counterintuitive.
If I say spreadsheet and then 5 minutes later say let's look at the tab, any human being instantly understands I am talking about the exact same object. Why does a hyper-advanced matrix of billions of parameters get tripped up by a basic synonym?
Well, the confusion arises because we fundamentally misunderstand how these models perceive language.
Okay, explain that.
They do not comprehend meaning the way we do. They process mathematical objects called tokens.
Tokens.
Yes. When you use the word spreadsheet, the tokenizer breaks that word down into a numerical representation. As the conversation progresses, the model's attention mechanism, specifically what we call the key value cache, builds a dense web of contextual weight around that specific token.
Okay, so it's tracking the math behind that specific word.
Exactly. It calculates the exact mathematical relationship between spreadsheet and every other word you have used in that session.
It's building a localized gravitational field around that specific string of numbers.
That is a highly accurate way to visualize it. Now, if you suddenly introduce the word matrix or tab as a synonym, you are not just using a different word.
You're throwing a wrench in the math.
You are injecting an entirely new, unweighted token into that mathematical environment. The AI cannot rely on human intuition to know they are synonyms.
It doesn't have common sense.
Right. It has to expend computational power to calculate. Is this new token a new variable? Are we discussing a mathematical array, the film franchise, a browser function?
Oh, wow. So it literally fragments the model's focus.
It forces the attention mechanism to divide its resources. The AI has to build a brand new relational web for the new token while still maintaining the old web for the previous token.
Which dilutes everything.
Exactly. When you are consistent in your vocabulary, you concentrate all of the contextual weight onto a single, deeply reinforced token. This leads to much sharper, highly deterministic output because the model isn't wasting probability cycles trying to merge competing definitions.
It is entirely about optimizing the machine's computational bandwidth. That completely changes the philosophy of prompting for me,
It's not a conversation, it's programming in natural language.
which aligns perfectly with the source's advice on building a prompt library. It acts almost like a senior engineer advising a junior developer here. It says to save your best prompts, stop reinventing the wheel and share successful templates with your team.
Treating prompts as functional code blocks is really the only way to scale this technology effectively.
Because if you write a Python script that perfectly sorts a complex database, you don't type it out from memory every single time you need to run it.
No, you save it as a function, you modularize it.
Right. When you lock in that perfect combination of persona, task, context, and format that yields a phenomenal result, you save that architecture.
You create a template. Help me with a blank task. Use the expertise of blank persona. The output should be blank format.
It removes the variance of human mood and human memory from the equation, giving you a stable foundation for rapid experimentation.
And you'll need to experiment.
Which brings us to what happens when the output inevitably fails. Because there is a massive, brightly flashing warning light in this guide.
Yes, there is.
He says AI output is a starting point, not a final product.
The necessity of human evaluation really cannot be overstated, particularly given how convincingly these models can hallucinate.
They sound so confident when they're wrong.
Incredibly confident.
So the guide offers 4 specific criteria for evaluating the output. Let's run through them. First is accuracy. Is the information factually verifiable?
Simple enough.
Second is relevancy. Did it actually adhere to the constraints of the prompt? Third is consistency. Is the structural tone uniform? And finally, bias. Does the output unfairly favor one perspective or demographic?
And that last point regarding bias really requires a technical understanding of the training data.
Because the AI isn't doing it on purpose, right?
Right. The AI does not have a moral compass or an ethical agenda. It has statistical weights based on the corpus of text it ingested during training.
And the internet is heavily biased.
Extremely. Since that corpus is heavily skewed by the historical biases present on the internet, the model will naturally output those same statistical biases unless explicitly instructed to counterweight them.
So evaluating for bias is not about, like, policing morality.
No, not at all. It is about ensuring the output is actually applicable to a broad, real-world audience.
Which brings up, I think, the most fascinating line in this entire section of the source. It notes that AI can be particularly prone to making mistakes when it is asked to navigate real-world knowledge and physical things.
The digital map versus the physical territory.
Yes. Because an AI understands the statistical relationship between the word apple and the word gravity, right?
But it has never dropped an apple.
Exactly. It doesn't know the physical sensation of weight or the friction of air resistance. It only knows the linguistic shadow of those concepts.
It's pure theory to the machine.
But before we explore how to cross that gap into the physical world, we have to look at the source's iterative techniques for fixing bad digital output. Because if you get a bad response, deleting the chat and giving up isn't the solution.
No, that's just abandoning the feedback loop. The first step is revisiting the structural framework we just discussed.
Checking the pillars.
Right. Usually a poor output is the result of a vague persona or missing context. But beyond simply tightening the bolts, you can utilize constraints.
Oh, the example they give for adding a constraint is brilliant.
It really is.
They add the line, provide solutions that can be implemented within a week.
Which is an incredible forcing function.
How did that actually change the math?
Well, by applying a severe temporal constraint, saying within a week, you immediately filter out all the theoretical blue sky multi-million-dollar strategies that these models love to generate.
Because they love to give you a 10-year plan.
They really do. But this constraint forces the probability matrix to prioritize practical, immediate, low-barrier actions. Constraints act as an incredibly effective pruning mechanism for the model's decision tree.
That makes a lot of sense. The source also heavily leans into the power of references, providing the AI with an existing example to emulate.
Yes, showing instead of telling.
Like, suppose you're trying to write a social media post promoting a local music festival. You could spend 20 minutes trying to describe the tone mathematically.
You'd be typing things like, make it sound energetic, somewhat sarcastic but welcoming, using outdoor terminology.
Which sounds like an absolute nightmare to prompt.
It's an exercise in futility. Stylistic nuances like breezy enthusiasm or welcoming sarcasm are highly subjective and incredibly difficult to articulate via abstract rules.
But the source suggests bypassing all that abstraction by simply pasting in a reference text.
Exactly.
It says, write a short social media post promoting a 2-day music festival. Use the following example as a reference for tone and format. Where mountains meet music, Indie Rock's festival returns, your favorite local bands plus national acts, good eats and sleep under the stars. Hashtag Indie Rocks, hashtag support local music.
Supplying a reference text is the equivalent of giving the model a highly localized compass.
It anchors it.
Yes. You are leveraging its strongest capability, which is pattern recognition. The model doesn't need to understand what indie enthusiasm means.
It just looks at the structure.
Exactly. It simply analyzes the structural skeleton of your reference, the use of the plus sign instead of the word and, the specific placement of the ampersand, the rhythm of the fragmented sentences, the density of the hashtags.
And it maps its new output directly over that stylistic scaffolding.
You are giving it the architectural blueprint rather than describing the building.
Now, there's one final mechanical concept we have to cover regarding AI before we transition to hardware, and that is the concept of the context window. The source states a very rigid rule here.
Yeah.
It says you must use new chats for new topics.
And to understand why that rule is absolute, we have to look at the underlying mathematics of attention mechanisms again, specifically what we call context bleed.
Okay, because if you are an experienced user, you intuitively know that you shouldn't brainstorm a marketing campaign and then ask for Python code in the exact same chat window.
Right. It gets messy.
But what is mechanically happening inside the model when context bleed occurs?
It comes back to the key value cache we discussed earlier. The context window is the finite amount of short-term memory the model can hold active during a single session.
It's working memory.
Right. Let's say you spend 45 minutes deeply refining a marketing campaign. You are discussing demographics, click-through rates, persuasive copy, ad
They
spend.
built a whole world.
The model's KV cache is now heavily saturated with tokens related to advertising. Those tokens have massive gravitational weight in the current probability matrix.
So the model's entire current reality is marketing.
Now, in that exact same chat window, you suddenly type, okay, let's brainstorm some entirely new product designs for a smart home device.
You've totally shifted gears.
But the model's attention mechanism cannot instinctively flush the previous 45 minutes of data. It doesn't know you consider that task finished.
It's still holding on to all those marketing tokens.
Yes. So when it calculates the probabilities for new product designs, the massive weight of those marketing tokens bleeds into the ideation process.
It starts dragging click-through rates into hardware engineering.
It will inevitably suggest smart home devices that are incredibly easy to market or devices that gather demographic data rather than devices that are structurally innovative or functionally superior.
Because its math is tainted.
Its probability calculations are corrupted by the residual data of the previous task. Starting a new chat is a hard reset.
It wipes the slate clean.
It completely empties the KV cache, allowing the attention mechanism to build a pristine, localized probability matrix tailored exclusively to the new problem.
Wow. Okay, so we have mastered the digital translation. We know how to bound the probability space with personas, optimize computational bandwidth with consistent tokens, use constraints to force practical outputs, and avoid context bleed by managing the cache.
We have effectively engineered a mathematically perfect digital thought.
But the moment you try to pull that thought out of the cloud and drop it on your physical desk, entirely new forces take over.
That's where it gets really interesting.
Because gravity, thermal contraction, and material density do not care about your vector embeddings.
Not even a little bit.
How does a machine translate a mathematically perfect token into a physical object without destroying it?
We are crossing the threshold from the pristine world of software into the unforgiving reality of hardware.
Which brings us to our second source, the apprenticeship manual for the Bambu Lab X1 Carbon.
A phenomenal piece of engineering.
The text immediately establishes a specific mindset shift. It states, the Bambu Lab X1 Carbon is just a 3D printer. In the world of industrial design, we view it as a high-fidelity prototyping station.
It deliberately separates this machine from the hobbyist toys that take days to print flimsy plastic trinkets.
And it breaks the machine down into 3 pillars to explain how it achieves this: the hardware architecture, the material science, and the intelligent workflow.
Let's dive straight into the hardware.
The text states that the X1C uses a Core XY motion system, which it labels the absolute gold standard for high-speed FDM printing.
The physics of the Core XY architecture represent a massive evolutionary leap over traditional desktop manufacturing.
Because historically, most 3D printers were what the industry calls bed slingers, right?
Right. They utilized a Cartesian coordinate system where the heavy print bed itself moves back and forth to create the y-axis.
Or the heavy motors were on the tool head.
Exactly. The dense stepper motors required to extrude the plastic were mounted directly onto the moving tool head.
So you had these massive blocks of metal being thrown around on belts.
It's incredibly inefficient for speed.
But the text claims the X1C achieves an acceleration of 20,000 millimeters per second squared. That number is staggering.
It's explosive.
Wouldn't throwing a heavy tool head around at 20,000 millimeters per second squared completely destroy the structural integrity of the plastic being laid down? How could it possibly be accurate at that speed?
Well, it would destroy the print if the mass was still there.
Oh, wait.
That is the genius of the Core XY system. It removes the mass from the equation.
How does it do that?
In a Core XY architecture, those heavy, dense stepper motors are unbolted from the moving axes and permanently anchored to the rigid, stationary outer frame of the machine.
So they don't move at all?
They stay completely still. The tool head, the part actually flying around laying down the molten polymer, is stripped down to be as lightweight as structurally possible.
It's like a sprinter taking off a heavy backpack.
Exactly. Suddenly, the acceleration is explosive. The lightweight tool head is driven by a complex interlocking system of long belts controlled by those stationary motors.
By anchoring the heavy motors to the chassis, you eliminate the massive inertia that causes the machine frame to vibrate and wobble when it tries to change direction suddenly.
Because vibration, the resonance, is the absolute enemy of precision.
If a heavy tool head tries to print a sharp 90-degree corner at high speed,
the momentum carries it past the corner, creating physical ripples in the plastic. We call it ghosting.
but by drastically reducing the moving mass, the Core XY system allows for that explosive 20,000 millimeters per second squared acceleration without the destructive inertia.
It fundamentally changes the pace of design.
And the source puts that acceleration into a deeply practical perspective for you. It notes that this speed allows industrial designers to iterate 3 to 4 times in a single day.
Compared to older Cartesian machines that would require 24 hours just to produce a single physical version of a prototype,
That shrinks the physical feedback loop down to the speed of digital iteration.
you aren't waiting until tomorrow to see if your CAD model works.
You are stress testing it by lunchtime. But moving fast is useless if the machine can't handle industrial materials. Which brings us to the hotend.
The business end of the machine.
The manual specifies that the X1C features an all-metal hotend with a hardened steel nozzle capable of reaching 300 degrees Celsius.
A very specific requirement.
So if we are talking to a listener who has only ever used standard PLA plastic on a basic printer, why does 300 degrees matter? And why hardened steel instead of the standard brass nozzles that conduct heat so efficiently?
Brass is an excellent thermal conductor, but it is a relatively soft alloy.
Right.
Standard PLA plastic melts around 200 degrees Celsius and flows through brass smoothly. But the X1C is engineered for advanced composites, which we will detail shortly.
Like carbon fiber.
Exactly. These advanced polymers are injected with microscopic jagged shards of carbon fiber or glass to provide immense tensile strength.
So pushing carbon fiber through a soft brass nozzle at high speed.
Acts exactly like liquid sandpaper.
Ouch.
Yeah. The microscopic carbon fibers will literally gouge and erode the inside of a brass nozzle within a few hours of printing,
Destroying the nozzle.
destroying its internal geometry and ruining the dimensional accuracy of the extruded plastic.
So the hardened steel nozzle is impervious to that microscopic abrasion.
It resists the wear entirely. Furthermore, high-performance engineering polymers like polycarbonate or nylon require an ambient melting temperature pushing 300 degrees Celsius simply to achieve a flow state.
So the hardware spec is not just a feature. It is the physical prerequisite for industrial application.
You can't print engineering materials without it.
That makes perfect sense.
Mm-hmm.
But the piece of hardware that truly shifts this machine from a dumb fabricator into an intelligent system is what the text calls the microlidor.
The eyes of the machine.
The manual states that this sensor scans the first layer of the print with 7 micrometer resolution to automatically calibrate the flow rate. Let's look at the physics of that. 7 micrometers is about 1/10 the width of a single human hair.
It's microscopic.
Why does the machine need a laser with that level of microscopic precision just to push plastic out of a hole?
Because molten polymer does not behave like water. It is a non-Newtonian fluid.
Okay, what does that mean in this context?
The viscosity of the plastic is a chaotic, constantly shifting variable. It changes based on ambient humidity, microscopic variations in the chemical composition of that specific spool of filament, and even the thermal ambient temperature of the room.
So it's unpredictable.
Very. When you push molten plastic out of a highly pressurized nozzle, it experiences something called die swell. It expands slightly as it exits.
So you can't just tell the motor to turn at a static speed and expect a mathematically perfect line of plastic to emerge.
Impossible. If the flow rate is off by even a fraction of a percent, you get microscopic gaps between the lines, leading to a structurally compromised part.
Or it extrudes slightly too much.
Causing the plastic to overlap and blob, destroying the dimensional tolerance.
How did people deal with this before?
Historically, human operators had to print dozens of hollow test cubes, measure the wall thickness with digital calipers, calculate the variance, and manually input a compensation multiplier into the software.
That sounds like a tedious analog calibration loop.
It was awful, but the micro lidar automates that entire process by creating a closed-loop feedback system.
Just like the AI feedback loop.
Exactly. It actively scans the microscopic topography of the extruded lines, measures the exact width of the die swell, and dynamically alters the stepper motor's extrusion multiplier in real time.
It is the physical equivalent of backpropagation in a neural network.
Precisely. The machine is analyzing its own physical output against the mathematical ideal, calculating the error rate, and adjusting its own parameters to achieve perfection.
It's grading its own physical homework.
It really is.
That perfectly bridges us into Section 4, where material science meets intelligent workflow, because as the manual explicitly states, as designers, we don't just care about how it looks, we care about how it performs.
Form follows function.
And function is entirely dictated by the chemical properties of the material. The X1C's enclosed, temperature-controlled chamber unlocks a huge library of advanced materials, and I really want to dive into how these specific plastics achieve their properties.
Let's go through the categories.
First, the composites. The manual lists PACF and PETCF.
Right. PACF is polyimide carbon fiber, essentially an engineering-grade nylon base matrix saturated with chopped carbon fibers.
And PEPCF.
That uses a polyethylene terephthalate base.
The industrial use cases listed for these are high-strength structural brackets and functional assembly line tools.
Okay.
How does suspending chopped carbon fiber in nylon actually increase the physical strength of the bracket?
Well, as the molten nylon matrix cools and crystallizes, the embedded carbon fibers form an overlapping microscopic structural lattice locked within the plastic.
Like rebar in concrete.
That's a perfect analogy. When a physical load is applied to the bracket, the stress is transferred from the relatively pliable nylon matrix directly into the rigid carbon fibers, massively increasing the part's overall tensile modulus and stiffness.
This is incredible. Next, the source lists engineering materials.
Yeah.
ASA and PC, which is polycarbonate.
Yes.
The use cases are UV-resistant outdoor enclosures and high-heat components. If you put a standard piece of ABS plastic outside in the sun, it turns yellow, becomes incredibly brittle, and shatters.
We've all seen old plastic lawn furniture do exactly that.
Right. How does the chemical structure of ASA prevent that ultraviolet degradation?
The vulnerability of traditional ABS plastic lies in its chemical backbone, specifically the butadiene rubber component, which contains double bonds.
Okay, double bonds.
Ultraviolet radiation from the sun possesses enough ambient energy to strike those double bonds and cleave them apart.
It breaks them on a molecular level.
Yes, severing the polymer chains and causing the plastic to physically crumble over time.
So what does ASA do differently?
ASA, which stands for acrylonitrile styrene acrylate, replaces that vulnerable butadiene rubber with an acrylic ester elastomer.
And that fixes the problem.
It does, because this acrylic ester lacks those reactive double bonds, meaning the UV photons have nothing to break.
Wow.
The polymer chain remains intact regardless of how much solar radiation it absorbs.
That is the exact kind of why we need to understand. If you are designing a sensor housing for a rooftop solar array, you cannot use ABS. You must dictate ASA in your workflow.
The chemistry dictates the application.
Now, moving past the aesthetic materials like PLA and PTG, which the manual notes are mostly for cheap, rapid visual mock-ups, we hit the most revolutionary category.
Support materials.
Yes. The text lists PVA and breakaway. The use case is complex geometries with internal voids or impossible overhangs.
Yeah.
We really need to address the fundamental physics of overhangs here, because this directly ties into the pro tip regarding the AMS, the automatic material system.
Right. The immutable limitation of all additive manufacturing is gravity.
It always pulls things down.
Always. You are building an object layer by layer from the bottom up. If your design features a severe overhang, say a bridge stretching between 2 points or a geometry extending out into thin air, the molten plastic will simply fall to the floor.
So the machine has to build a temporary sacrificial tower of scaffolding underneath that geometry to support the molten polymer until it cools and hardens.
Exactly.
But in traditional single material printing, that scaffolding is printed using the exact same plastic as the final object.
Which is a huge problem.
Because when the print finishes, you have to grab pliers and violently rip that scaffolding away, which inevitably leaves jagged scarring and damage tolerances on the surface of the print.
It fundamentally limits the geometric complexity of what a human can design. You avoid overhangs because you hate removing supports.
But the AMS, the system that sits on top of the X1C, allows the machine to actively slice and splice up to 4 different spools of filament during a single print.
It changes everything.
And the manual is adamant that the AMS is not just for printing multicolored toys. It is an industrial tool for managing support interfaces.
Yes. The pro tip details a workflow where you print the massive bulk of your main part and its scaffolding out of a strong, cheap engineering plastic.
To save money and time.
Right. But you instruct the machine to switch filaments and print just the top few microscopic layers of the scaffolding, the interface layers that actually touch the final part out of a completely different chemical material.
And that is where PVA comes in.
Right. PVA is polyvinyl alcohol. It is a synthetic polymer that is entirely water-soluble.
Wait, water-soluble?
Yes. So you print a complex, geometrically impossible internal void using PVA support interfaces. When the print is done, you don't use pliers. You drop the solid block of plastic into a bucket of warm water.
And it just dissolves.
The interface layers chemically dissolve into a harmless liquid, and the solid scaffolding simply falls away,
leaving a mathematically pristine surface finish on an internal structure that a human hand could never even reach.
Exactly. Or you use breakaway material, which is chemically formulated to have zero adhesion to your primary plastic.
So it functions like a microscopic layer of Teflon.
You snap the supports off with zero resistance and zero scarring.
By manipulating the material chemistry, you completely remove the physical constraint of gravity from the design process.
You can design geometries that would be literally impossible to manufacture via traditional injection molding or CNC milling.
But to manufacture those geometries, the workflow, the software handshake, has to be perfect.
It has to be flawless.
The manual drops a massive bombshell here regarding how we send digital CAD models to the printer. It states, emphatically, stop using STLs.
A very aggressive mandate for a technical guide.
Yes, it says Bambu Studio, the slicing software, supports step files natively, and that step files preserve the true mathematical curves of your CAD design, leading to smoother prints and better dimensional accuracy.
What's fascinating here is the mathematical difference between those two formats.
Let's dive deep into the math here. What is the fundamental difference between an STL file and a step file? Because this perfectly mirrors our earlier discussion about using precise, consistent tokens when prompting an AI.
The parallel is exact. The STL file format is a digital relic from the 1980s.
Wow, that old.
Yes. When you design a perfectly smooth, curved object, say a precise mechanical sphere in your CAD software, and you export it as an STL, the software physically cannot process true mathematical curves.
So what does it do?
To save file size, it approximates the curve by tessellating the surface. It breaks the smooth sphere down into thousands of microscopic, flat, rigid triangles, a mesh.
So a sphere basically becomes a highly detailed disco ball.
Exactly. And no matter how high the resolution, no matter how tiny you make those triangles, it will never be a true curve. It is a faceted approximation.
So when the printer reads it,
When the printer software reads an STL, it translates those flat triangles into linear paths for the motors. The machine literally prints microscopic flat edges instead of a sweeping curve.
introducing surface imperfections and ruining the dimensional tolerance of press-fit mechanical parts.
Right. It is the physical equivalent of giving the AI vague, approximate vocabulary. You are telling the machine, make it sort of round-ish.
But a step file is different.
Very different. A step file format utilizes NURBS non-uniform rational B-splines.
It does not use flat triangles.
No, it preserves the absolute underlying mathematical equations that define the curves generated in the original CAD software.
So when the slicing software reads a step file,
It translates those pristine algebraic equations directly into perfectly smooth, continuous arc movements for the core XY motors.
by using a step file, you are removing the translation error. You are communicating with the hardware in the native language of geometric precision.
You are giving it the exact mathematical truth.
Now, speaking of native intelligence, the manual highlights two final software features that demonstrate the immense computational power running locally on this machine. First, AI monitoring.
Ah, the spaghetti detective.
Right. The text notes that the X1C utilizes an internal MPU, a neural processing unit, to detect spaghetti.
Which is the colloquial industry term for a catastrophic print failure, where the plastic loses adhesion to the bed and simply extrudes into thin air.
Creating a massive tangled nest of molten string that ruins the part and can physically damage the hotend.
It's a disaster.
The manual frames this as a workflow savior. You can start a 20-hour engineering print, leave the facility, and receive a push notification on your phone if the print fails, saving hundreds of dollars in wasted carbon fiber filament.
But computationally, think about what is required for a machine to detect that failure.
Yeah, how does it know?
It requires immense localized processing power. The machine has an internal camera continuously feeding frames to the MPU.
So it's watching it print.
The MPU is running a visual recognition model that must actively distinguish between the complex, chaotic geometric shape of a legitimate print that is currently being built and a chaotic tangle of failed plastic.
It's performing real-time visual analysis and calculating failure probabilities at 30 frames per second.
Locally on the machine.
And then there is vibration compensation. The manual states that before every single print, the machine literally shakes itself to tune its motors, eliminating ringing or ghosting artifacts.
This is brilliant engineering.
How does shaking the machine prevent vibrations during the print?
It relies on the physics of resonance frequencies.
Okay, break that down.
Every physical object has a natural frequency at which it vibrates most intensely. For the printer, that frequency changes based on the mass of the filament spool currently loaded, the specific density of the desk it is sitting on, and even the ambient temperature.
So it's different every day.
Exactly. Before the print starts, the machine runs a sweep of intense vibrational frequencies through the tool head and measures the frame's physical response.
It is mapping its own physical vulnerabilities.
Right. Once it calculates its unique resonant frequency for that specific moment in time, it utilizes active resonance compensation.
What does that mean for the motors?
It mathematically injects precise, inverted counter frequencies into the motor commands during the actual print.
Oh, wow.
As the toolhead whips around a corner and generates an inertial wave that would normally cause the frame to shudder, the motor simultaneously generates an opposite wave that perfectly cancels the momentum out.
It is the exact same physics used in active noise-canceling headphones, but applied to massive physical momentum.
It is literally tuning its own physical instruments before the symphony begins.
It is an astonishing level of automation. But, crucially, the manual ends with a severe reality check.
It always comes back to reality.
The final section is your first assignment. The master is giving the apprentice a test. And the test isn't about configuring the NPU or trusting the LiDAR or relying on the AI.
No.
The test is about deeply understanding physical limits. It tasks the user with testing bridging intolerance and learning DFM rules.
Designed for additive manufacturing.
Things like handling 45-degree overhangs or calculating shrinkage for press fit assemblies.
Because at the end of the day, no matter how flawless your step file is, no matter how fast the core XY motors accelerate, and no matter how precisely the micro LiDAR calibrates the non-Newtonian flow, physics always wins.
Gravity and heat always win.
Thermodynamics dictate that a plastic part extruded at 300 degrees Celsius will inevitably contract and shrink slightly as it cools down to a room temperature of 22 degrees.
The ultimate unavoidable constraint.
If you require two carbon fiber parts to press fit together perfectly to form a watertight seal, the smartest machine in the world cannot save a mathematically flawless CAD design that ignores thimble contraction.
Because it's going to shrink after it's done.
Exactly. The human designer must mathematically calculate that specific material's shrinkage coefficient and manually oversize the internal geometries of the CAD model before exporting the step file.
You must design for the manufacturing process.
Human understanding of physical limitations, Physics, shrinkage, gravity remains the ultimate constraint that AI cannot bridge alone.
So when you look at your own workflow, what does this all mean for you?
It's the big question.
We have journeyed from bounding the infinite probability spaces of large language models to managing the thermal contraction of physical hardware. But whether you are writing a prompt for Gemini, carefully balancing your persona, task, context, and format to avoid context bleed, or you are slicing a pure step file for an X1 Carbon, you are acting in the exact same role.
You are the director of powerful intelligence systems.
You are the orchestrator of intent. Success relies on clear intent, structured communication workflows, and relentless, informed iteration, both digital and physical.
You evaluate the generated text against your constraints. You measure the physical print against the thermal reality.
You close the gap between what you vaguely asked for and what you precisely wanted.
But there is a final thought here, something that builds upon the convergence of everything we have discussed today, that points to where this entire ecosystem is inevitably heading.
What's the logical conclusion of all this?
Well, we have spent this deep dive treating these systems as parallel tracks, right? We use the AI to brainstorm the digital idea, and we use the highly intelligent 3D printer to physically manufacture the human's design.
Right.
But what happens in the very near future when those two systems are integrated, when we close that loop completely?
Walk me through what that looks like.
Imagine applying that perfect prompting framework to instruct a multimodal AI, not just to write a marketing tagline, but to generate the actual step file for a structural bracket.
Right.
And what happens when that AI is granted API access to send that step file directly over the cloud to the X1 Carbon?
It bypasses the human slicing software entirely.
The X1 Carbon receives the file, heats the hardened steel to 300 degrees, and prints the bracket out of polycarbonate. But then it uses its microscopic LIDAR array and its internal neural processing unit not just to check for spaghetti, but to physically analyze the structural integrity and dimensional accuracy of that printed part against the original math.
Oh, wow. It detects a microscopic flaw.
It detects where the bridging sagged due to gravity or where the thermal shrinkage caused a dimensional error of a few micrometers.
The machine performs the reality check.
But instead of sending an error notification to a human's phone, the machine feeds that microscopic physical evaluation data directly back into the AI's context window.
It tells the AI what went wrong physically.
The AI analyzes the failure, mathematically recalculates the thermal shrinkage coefficients, dynamically alters its own internal CAD geometries, generates new, improved step file, and triggers the printer to try again.
The AI becomes a completely autonomous engine of physical evolution.
The line between software iteration and physical evolution is about to disappear entirely. The system isn't just grading its own homework, it is writing the curriculum, taking the test, analyzing the physics of its failure, and rebuilding the school until it achieves perfection.
And the only thing it requires to start that infinite loop of autonomous physical creation is that very first, perfectly engineered spark of human intent.
It brings us right back to the beginning.
The genie in the lamp. Except very soon, the genie won't just be granting your poorly phrased wish. It'll be evaluating its own magic, testing its own work against the unforgiving laws of physics, and granting its own iterative wishes until the physical reality precisely matches your digital intent.
The only question you're left with is,
what are you going to ask it to build?